Thank you, Serena, and thank you to all the organizers. It's a great pleasure to be here. It's my first time at the Institute and meeting many of you. So today I'm going to talk about a recent project that I did with my former postdoc mentor, Dennis here, at Rutgers University. And he was actually the one introducing me to this problem, so I'm very thankful. I think it's a very nice free boundary problem that it might not be as known as other free boundary problems like Bernoulli or Stefan problem, but there's many interesting questions here that are still also open. Okay, so let me start with a brief introduction. So just some motivation where this model that we study appears, for example, in ground filtration. So we have here a system of groundwater. Okay, so we have a house. The house gets its filtered water through this system. Okay, and the water here mostly comes from just the rain. And it's stored here under the soil. Okay, so how it works is it rains, the water travels through this region. Okay, so this is mostly made of sand and gravel. Okay, so it travels through these porous spaces until it reaches this saturated zone. Okay, so here the medium cannot absorb more water and it's completely saturated. Okay, so we have these two regions, the unsaturated and the saturated one. Okay, and so we want to keep track of the water level, okay, because we're interested in not running out of water. Okay, we want to always have water here in this system. Okay, so this is sort of the application. Now, what is the actual model? So there's two main ingredients here. First, the pressure, okay, the pressure of the water. And this is given by this function u, which depends in space and time, which is the unknown of the problem. And then we also have this function, C, which is given, and this measures the saturation content, okay? So how saturated is the medium? So if C is 0, then it's completely unsaturated. If C is 1, then it's completely saturated, okay? And this is, again, this is a given function. So after some simplifications, okay, some reductions, the continuity equation and Darcy's law give the relationship between the saturation function and the pressure, okay? So it's this very nice equation. And to determine the behavior of this function C, there is an empirical law, which tells us that C is identically 1, C of U, okay? So this means the medium is completely saturated whenever U reaches and surpasses this saturation pressure, okay? U sub S. And then whenever U is below the threshold, the saturation or the derivative is strictly positive, meaning that the saturation is strictly increasing. Okay? So this is the physical model. Now to study it, if we want, we can make some simplifications. Okay? So we're going to assume that this threshold is just 0. Okay? And it will also be convenient for us to make this change of variables. Okay, so from now on, the function C will be identically 0 whenever U is less than or equal to 0. And then the derivative will be strictly positive whenever U is positive. Okay, so this is an increasing function. And the example that I want you to have in mind is precisely this one. Okay, so C of U is the positive part of U. And this is what we will actually consider in the future. Okay, so this function satisfies that it's 0 here, and then it's strictly increasing when U is positive. Okay, so this is the equation that we study, and we can formally differentiate this with respect to t, right? We can take the derivative here inside. And so what we get is that in the positive phase, okay, so in this unsaturated region, U satisfies this parabolic equation. Okay, and this, in the reference example, when C of U is the positive part of U, this is just 1. So U satisfies the heat equation. Okay? Now, in the negative phase, we lose information about the time derivative, right? This is 0, and so U satisfies the Laplace equation. So U is a harmonic function. Okay, and so we're interested in the 0 level set, which is this interface, like we saw in the picture, that separates the saturated and the unsaturated regions. Okay, and we want to know more about this interface and about the regularity. Okay, so as you can see, this is a two-phase problem, but it's very different than the classical models, right? We have two different types of equations on each side. We have an elliptic equation and we have a parabolic equation. So this is why it's called an elliptic-parabolic three-boundary problem. Okay, and we're going to see what kind of challenges arise in this type of model. So before, I just wanted to briefly comment on some related models where this type of equations appear. So for example, the conductivity problem. So this is given by, so it's a model where C of U is given by this piecewise linear function. It's a function that looks like this. Okay, so it's just like that. This is U equals 0. Okay, so it's a piecewise linear function. On each side, right, on each phase, we get a heat equation, but with different time scales. Okay, and these models typically describe, for example, heat propagation through composite materials. Okay, and what's also interesting about this model in relation to the elliptic parabolic problem is that when you take A plus, so one coefficient equal to 1 and the other one equals epsilon, right? So this is converging, the slope is going to 0, and it's converging to this elliptic parabolic problem. Okay, so it's, let's say, another motivation where these type of problems arise. Second example that I think it's classical by now, it's the porous medium equation. Okay, so this describes, in this case, the fluid flow through a unsaturated, so completely unsaturated porous medium. And the density, U, is modeled by this equation, but typically it's written in this form. Okay, so C of U is this concave function, and well, people study this type of equations. There's a lot of literature in this topic, and nowadays it's well understood, at least in this classical form. Okay, and then the last example that I wanted to mention, it's the Stefan problem. So this is maybe one of the most famous parabolic problems. We have a few experts here. And in this case, this formally, you can describe, so this is the evolution of a solid-liquid interface, right, like ice melting in water. And you can describe it with this model. So it's like this function here, but with a jump, right? So something like this, maybe. Has a jump discontinuity here, and there's many difficulties that arise in this problem, and this is still a very, very active research topic. Okay? Okay, so let's go back to the elliptic parabolic, and I wanted to discuss what are some of the challenges that we encounter here. So the main difficulty of this model, as we saw, is that the parabolic equation degenerates in time in the saturated region. Okay, so in the negative phase, we have the Laplace of U is equal to 0, but U is a function of space-time. So we lost all the information of the time derivative that we had in the positive phase. Okay, so T here only acts as a parameter, nothing else. Okay, and so as a consequence, one of the consequences is that we're not going to get any time regularization in this region. Okay, so U will be, the best regularity you can get for U in the negative phase is the one that you prescribe on the boundary data and the one coming from the parabolic phase. Okay, so it's not going to regularize. And another consequence that I think is interesting is that you can actually construct solutions that are discontinuous in time for this problem. Okay, and I'm going to give you a couple of situations, and we will see also a couple of examples where this can happen. But for example, you can see discontinuities in time if you have a model where the parabolic phase collapses. Okay, so in other words, the medium becomes completely saturated. And at that time, the pressure is going to jump. We will see an example after this. Okay, so this is one example. And another one, it could be by global reasons. Okay, so let's say you have a boundary data on the elliptic phase that has a jump. Then what happens is that the jump propagates to the interior. So you get a jump discontinuity in time, okay? So these are a couple of situations where you can get discontinuous solutions. And what I wanted to emphasize here is that due to this global nature of the problem, it is difficult to prove local properties of solutions. Okay. So let's see a couple of examples where this can happen, just to illustrate better the situation. Okay. So first, when the medium becomes completely saturated. Okay. So the situation here is this is a 1D flow. The domain is -1, 1. Okay. And the boundary data is constant -1, let's say. Okay. So we start with this blue profile over here, this kind of tent, and then we let it evolve. So what happens? Okay, so in the positive phase, where U is positive, the solution instantaneously regularizes, right? It satisfies the heat equation, so this is a smooth function. And then in the negative phase, this is a harmonic function, so it's a couple of lines, okay, that attains the boundary data. Now, since we started with a profile that it's concave, the flow is going to, so U will be monotone decreasing in time. Okay, so what's happening is that the parabolic region, right, this interval here, is shrinking. Okay, so the parabolic phase is shrinking until it shrinks to just 1 point. Here we still have harmonic function on each side, right? And then right at that time, where it T sub S, right, when the medium becomes completely saturated, the parabolic region disappears, and so U wants to be just harmonic. U wants to be a harmonic function that attains the boundary data, which is constant -1. So it's just going to be -1, just constant, okay? So you see from the orange profile to the red one, I hope you can see colors, by the way. So from this color to this one, you get a jump discontinuity. Okay, so this is one of the possible situations. Now let's discuss the other one. So here we don't have a picture of the solution, we have a picture of the domain. Okay, so again, it's a 1D flow. The domain is -1, 1. Okay, this is the time axis. And so we can, like I said, we can have discontinuous solutions whenever we have boundary data that is discontinuous in time. Okay, so here we are prescribing -1 up to the 1/2 and then -2. And then on the right boundary, we're prescribing just 1, positive. We don't care about the jumps here because, as we know, in the interior, it's going to regularize, okay? So we just care about the jump here. Okay, and then as an initial data, we're going to just consider the function x, because this attains the boundary data, okay? And it's actually a solution of the equation, right? This is a harmonic function, satisfies the heat equation. So up to 1/2, the solution is just going to be x, right? The free boundary here is not moving. And then right after, the boundary data changes. So of course, if there's a jump here, it will propagate here inside in the negative phase. Okay, so we will see a time discontinuity here. Now, what I think is also interesting about this model is what happens here. Okay, so I'm sort of spoiling the answer already, but this is something that Dennis and I studied. Okay, how is the interface behaving at the point of discontinuity? And we will see that it's going to be locally like a square root of t. Okay? So we will come back to this example later. Okay. A little bit about the history of the problem. The analysis started around the 80s, and most of the works are for one-dimensional flows. Okay, there's also a few for higher dimensional flows, but it's mostly for one-dimensional. And the pioneers of this theory are Van Duyn and Pelletier. And in 82, they studied this model here. Okay, so it's a 1D flow. And they study a Cauchy problem with constant Dirichlet data. So they have -1 when x is equal to -1, and they have +1 when x is equal to 1. Okay, and then for this model, they introduce a notion of weak solution, and then they develop all the theory. Okay, so existence, uniqueness, and regularity. And also Van Duyn proves around the same time the continuity of the interface. Okay, so here, since we have negative on one side, positive on the other side, we know that there will exist an elliptic phase and a parabolic phase, and then there's this interface that separates these two regions, okay? Assuming some conditions in the initial data. Okay, So this is the constant Dirichlet problem, and then a few years later, Khrushchev and Pelletier extended these results to more general boundary conditions. Okay, so they consider boundary conditions of this type. So for example, if B is 0 here, then this is a non-homogeneous Dirichlet condition. Okay, so it's extending the results that Van Duyn and Pelletier proved in '82. And also when A is 0, then this is a Neumann type condition. And then, of course, the Robin type, okay? So here it was important for them, and I will come back to this, that F is a Lipschitz function. Okay, so they developed the same program that they did here for this type of boundary conditions. And then there's also a few results on higher regularity, assuming more assumptions by Birch and Khrushchev. Okay, now for higher dimensional flows, there's this work by Di Benedetto and Gariepi in '87, where they actually proved a local result. Okay, and this was the only local result available. So we know that U does not have to be continuous, right? I mean, it really depends on the boundary data you're prescribing. However, the function C of U is continuous. Okay, and this is a local property. So if you want, if you think about the reference example, this is telling us that the positive part of U is continuous. Okay, the negative could be discontinuous in time, but the positive is always continuous. Okay, and then Khrushchev and Bolansky, for higher dimensional flows, they studied monotone flows. Okay, and they obtained that under this monotone configuration, the free boundary is a Lipschitz graph. Okay, so this is what's known about the regularity of the free boundary in higher dimensions just for monotone flows. And a more, say, recent result, so this is 2013, by Kim and Potzart, who consider, so they pose the problem in the setting of viscosity solutions, okay, and they consider these more general solutions with fully nonlinear operators here, right? So they replace the Laplacian by this more general operator, and they prove the existence. Prove existence of viscosity solutions, and I think regularity is open for this problem. Okay, so this is one of the last results that work on this problem. Okay, so from now on, we're going to focus on just one-dimensional flows. Okay, and I want to be a bit more precise on the results that were proven. Also to motivate better what we did, okay? So let's focus on the Cauchy-Dirichlet problem, okay, with two functions, f of t and g of t. And we're going to assume that, so the function c satisfies this elliptic-parabolic condition, okay, that we saw before. The functions f and g, the boundary data, are going to be Lipschitz and satisfy this sign condition. Again, the sign determines that, so it guarantees that there will be an elliptic and a parabolic phase, okay, and they coexist. And then for the initial condition, we're going to assume that there is a function that's Lipschitz, U0, that satisfies this condition, okay, doesn't have to be unique, and it attains the boundary data. Okay, so if you want, this is like saying that the positive part of U0 is this given V0. Okay. So as you see, this is so we're assuming that everything is Lipschitz, and under these assumptions, what can we say, or what did they prove? Okay, so first, the definition of weak solution that was introduced by Van Duyn and Pelletier. So this is an L2H1 function, okay? The saturation C of U is continuous in time with values in L2. The boundary data is attained for almost every time, okay? And then it satisfies this, U satisfies this identity. So this is the typical identity where you multiply the equation by this function and then integrate by parts in space and time, okay? So the spaces here rise naturally from making this work, okay? So for making sense of this. Okay, so this is the notion of weak solution, and what is a summary of classical results for weak solutions? So first of all, there is a unique weak solution to the Cauchy-Dirichlet problem. Moreover, they can improve the regularity whenever the boundary data is Lipschitz, okay? So they can show that, so UX is uniformly bounded in space and time, and uxx is an L2 function, okay? And then the saturation function C of u is continuous. And this is independent of the boundary data, okay? This is a local result. Okay, what about the free boundary? So here, what they prove is that if the initial condition satisfies that it's 0 to the left of some number or not, and then it's positive to the right, okay? This is to say that the interface starts at that point, and then it's just going to be a continuous function, okay? It's going to be a continuous function, so the zero level set is given by the graph of this function R, okay? So this is really a sharp interface that separates the positive phase and the negative phase. And in fact, under more conditions on the initial data, they can show, and the function C, they can show Lipschitz and C1 as well. Okay, now, in all of these classical articles, the main strategy to prove these results is to regularize the problem, right? So you have the function C of u looks like this. So again, we lose information about the time derivative here, so we can just make this smooth and something like that, right? So that C prime is positive. Okay, so now I have a uniformly parabolic equation, okay, for the regularized problem. I can regularize the data as well, and so I get a smooth solution. Okay, so then everything boils down to obtaining uniform estimates for this approximating problem. Okay, and so these are the properties that are preserved at the limit for them. Okay, and what I really want to emphasize here is that these estimates depend on the Lipschitz norm of the data. Okay, so they develop all of this theory, and they need that the boundary data and the initial data is Lipschitz. Okay, and so we can ask, well, what if they are not Lipschitz, right? Even what if they are discontinuous, even? Okay, so this is something that Dennis and I studied, and in particular, we were interested in answering this question. So this was our main goal, right? So if for some global reasons, like we saw in the second example, we have a jump in the elliptic phase, okay, in the negative phase, what are the local effects of this on the interface? Okay, what is happening to the interface whenever we have a jump on the elliptic phase? So this is what we're going to try to answer today. Okay, so we're going to assume very mild assumptions. Okay, we fix two universal parameters, little lambda and capital lambda. And for simplicity, we should just take C of u to be the positive part. Okay, this function already captures all of these essential features that we want to study. Next, we assume that on the boundary, so at x equals -1 and at x equals 1, u, so on the left, u is bounded by these negative constants, and on the right, u is bounded by these positive constants, universal constants, okay? And then the initial data, we also assume it's bounded, okay, by lambda, and it satisfies this condition, okay? So it's 0, the positive part is 0 for x negative, and then it's positive for x positive. And again, this is to guarantee that in the future, the interface will be a graph, okay? All right, so under these conditions, we can construct approximating solutions, okay? So here we need two steps. We need to modify all this data, and then you can just, you can regularize if you want everything and pass to the limit, or you can just apply the classical theory, okay? So if we regularize the data and we have that everything is Lipschitz, and we are under the conditions of these classical papers, then we can construct an approximating solution. Okay, so we have approximating solutions to this problem. And so the question again is, okay, what are really the properties here that we can obtain when passing to the limit? Okay, and so this boils down to proving estimates that only depend on these universal parameters, nothing else, right? We don't have continuity, we don't have Lipschitz, I mean, we just have these bounds. So what are really the properties that we can show that depend only on these parameters? Okay, so that's the goal. Okay, so it turns out that thanks to these classical results that we already have in hand, for the approximating solutions, we can show that they satisfy this elliptic-parabolic free boundary problem. Okay, so there is so the free boundary is given by the graph of a function R. Okay, to the left of this interface, U is harmonic. To the right, U is caloric, and then U satisfies, or well, there's this free boundary condition. Okay, this is like saying that U is C1. Okay, but this is not satisfied for all times. This is satisfied in the strong sense. Okay, so this is for almost every time. Okay, so really here, the advantage of working with 1D flows for the key simplification is that harmonic functions are lines. Okay, so if U satisfies this equation here, we have a representation formula for the solution. It's just a linear function in space with these time coefficients. Okay, so this is really giving us a lot of information already. And so we need to study, okay, what happens on the parabolic phase, right? There's a connection between the elliptic and the parabolic phase through the free boundary condition. So what can I say using this information? So if you differentiate here with respect to x, you get this slope, which, by the way, this is positive because f is negative. Okay, so you get this condition. And so what we see is that in the positive phase, right, again, this is the unsaturated region, U satisfies this free boundary problem. So it satisfies a heat equation in the positive set. And then it satisfies this kind of Neumann type condition on the free boundary. Okay, and this is a parabolic Bernoulli problem. The elliptic counterpart has appeared several times in this conference. But here, the data here is just in L infinity. Okay, and in fact, this type of problems have been studied by several people. So this in higher dimensions, right? When this is constant. Okay, this appear, for instance, in the propagation of flames. So there's a few works in the late 90s and early 2000s where they study these parabolic Bernoulli problems. But I think for L infinity data, as far as I know, not much is known. And so I think it's an interesting problem by itself. Okay, but we're not just going to focus on these. We're going to use the information that we know also about the elliptic phase. Okay, we're going to work with both phases, not just with the positive phase. Okay. Good. So what are our main results? What do we show about this problem? Okay, we have a weak solution to the equation, and these are the assumptions that I stated before with these parameters little lambda and capital lambda. Okay, so we show that there's these universal constants, universal meaning that they only depend on the universal parameters, little lambda and capital lambda, such that, so we prove three things. About the regularity of the solution, we show that the spatial derivative is bounded, okay, almost everywhere, by this universal constant. And moreover, in the positive phase, right, so this is the function C of U, we can improve the regularity in time. Okay, so in the negative phase, we're not going to be able to improve it. But in the positive phase, since U satisfies a heat equation, we do expect some improvement in the time regularity, and we show that it's C1 halving time. Okay? Now, a second property that was actually crucial for us is this non-degeneracy property. Okay, so we prove that the spatial derivative is strictly positive. Okay? So it's bounded below by this universal constant in a neighborhood of a free boundary point. Okay, and this, we will see this is fundamental because this monotonicity will allow us to use certain tools to study the free boundary regularity. Okay? And then finally, let's say that the main part of the theorem is the free boundary regularity. So we show that, so for future times, by the way, Q1 here is just the unit rectangle, okay? And Q1 half is half of it, let's say. So a little bit more in the interior. The free boundary is given by the graph of this function, okay? So this function is continuous. The value, so it does not hit the lateral walls, okay? And there's like a universal bound here. And moreover, it's C1 half, Okay? The C1/2 norm is also bounded universally, and this is the optimal regularity. Okay? So several things. It's graphical, it's given by a continuous function that is in fact C1/2, and this is optimal. Okay, so this third part here answers the question that I posed before. Okay, so how does the interface behave when you have a jump discontinuity on the elliptic phase? And this is the answer. Okay, so in the time that I have left, I wanted to discuss some ideas of the proof, and I know it's the last talk of the day, and you might be a little bit tired, so it's mostly going to be some pictures and a few details. Okay? So first, a couple of tools that are useful in the proof. So an energy estimate. Okay, so we show that for weak solutions, the L infinity L2 norm of C of U and the L2 norm of the spatial derivative are bounded by the L2 norm of U. Okay, so this is, I would say, maybe like a standard estimate that comes from the equation. And by the assumptions, we know this is universally bounded, so we get that these quantities are bounded universally. Okay, and this will be useful. And then a second tool, which is very important, is that, okay, so for the approximating weak solutions, we know that, maybe I can explain here a little bit better. So this is our domain. Okay, this is x equals -1, and this is x equals 1. Okay, and this is the time axis. So t equals, let's say, -1, t equals 0. Okay, so we're prescribing here that u is negative, right? So it's bounded by some universal constants. And then we're also prescribing here that u is strictly positive, okay? So we know for the approximating weak solutions that if u is equal to 0 here, then there's going to be a curve, right, that gives the free boundary. Right? So the free boundary is given by a curve. Now this cannot hit the wall, right, because u is continuous up to the boundary for the approximating solutions, and this is negative. Okay, so this cannot happen. Now the question is, can I show for the original solution that this is separated uniformly, right? Only depending on these bounds. I mean, this is really the key thing. And this is what we show here, okay? So we show that there's two universal numbers. So delta 1 is the lower bound, delta 2 over here, such that the free boundary we don't know what it will do, but it will be away from the lateral wall, okay? So this is what this is saying. And, okay, and the proof is you construct some sub-solutions, some super solution, and use comparison arguments. Okay, okay, so let's talk about the Lipschitz estimate. So the spatial derivative is bounded by a universal constant almost everywhere. One thing to notice here is that in the elliptic phase, so when u is negative, we have this representation formula. U is linear, okay? And so the slope was, so if you remember, ux is equal to minus f of t, 1 plus r of t, okay? So this is true here. Now this f is bounded between these two constants. So this is universally bounded. And now, because we know that r does not hit, so there's like a universal separation here, this will also be universally bounded, okay? So on the free boundary, we know that this is bounded by capital lambda over delta 1, okay? We have that bound, okay. And this is also true everywhere here. So we want to prove the estimate here. We want to prove the estimate in the parabolic phase. Okay, so thanks to the free boundary condition, this will be true here. Now what happens here? Well, over here, so in this line, we use interior estimates for the heat equation, right? Because again, we know this is a uniform distance. So we know that ux will be bounded by 1 over the distance, which is delta 2. And then the L2 norm, it's also bounded by capital lambda. So we have the bound for this boundary here. Okay, so last, what's going on over here? Well, maybe we don't have that ux is bounded here, but it will be in the future. So we know that ux, by the energy estimate, it's in L2 here, and we have a uniform bound. So the local in-time maximum principle tells us that, okay, well, if you know it's in L2 here, right? It's bounded universally, and we also know that over here and over here, we have the universal bound. Then a little bit more in the future, so after this dashed line, in this region, it will be universally bounded. Okay, so that's it. That's the proof. Okay, and once you have this Lipschitz estimate, you can do more things, like you can improve the regularity in the parabolic side. So here, this kind of comes from the scaling of the heat equation. So if you have one derivative in space, you have 1/2 derivatives in time. Okay, and this is probably a bit maybe standard if you work in parabolic theory. I think it's a nice proof. So you prove it by comparison with a global barrier. Okay, so what you do is you want to prove, so you want to control the difference of u here and u here. So u here minus u here has to be bounded by the square root of the difference of the times. Okay. Now you already know that u is Lipschitz. So at, let's say, T1, the smallest time, you know that u will be below this blue absolute value, the graph of u, okay? So what do? You take the solution to this, to the heat equation, okay, in all of R, which starts at, so you have to choose these parameters, okay? You choose A, B, and T0, you choose T0 equals to T1, and you put something here that it's above, right? Let's say you want to prove the bound from above. Now, you put something that's above. By comparison, u will be below the barrier function phi. And then you can use the heat kernel. So you can use the representation formula for these global solutions that have this type of initial conditions and check that they also over this axis, they are exactly equal to essentially square root of so T2 minus T1. Okay, so this really comes from the behavior of the global solution to the heat equation. And you can do the same thing from below. Okay, so that's the proof of the improvement of regularity in time. So moving on to the second result, the non-degeneracy. So like I said, this is one of the, I would say, most important results, and the proof is a little bit more delicate. So here, let's say we are in this localized situation where, so you fix a point in the free boundary, and then you look in a box around it, okay? And then you assume that this is 0, 0, okay? And you want to show that over here, ux satisfies this non-degeneracy property. So it's bounded below by a universal constant, okay? So a few remarks here. Again, in the elliptic phase, this is true, right? So we have this formula, and f is bounded below, r does not hit the wall, so we have the lower bound. Okay, and so also by the Lipschitz estimate, we have a lower bound, but it's not good enough, right? I mean, we want this to be a positive constant. So we need to improve this lower bound in the parabolic phase, okay? And this is done in 3 steps. So first step is, okay, the idea is here, if, let's say, I already knew that my free boundary is sufficiently nice, you can expect that u is monotone, right? Like Hoff lemma. So it's 0 here, positive here, and so it's ux has to be strictly positive, and we want to get this universal bound. Now we cannot use Hoff lemma because we don't have enough regularity here. Okay, we don't know how the 0 level set is, but we can look at other level sets of caloric functions that are close to to the zero level set. Okay, so this is the idea, because we know a lot about level sets of caloric functions. So we're going to fix an A level set. Okay, we know this set is non-empty because U is 0 here, and it's greater than lambda here. Okay, so there has to be an A, so this will be non-empty. We also know that this set will contain a finite number of smooth curves, and by strong maximum principle, they cannot be homeomorphic to a circle. Okay? And one more property, which is by continuity, we know that one of these curves has to disconnect the free boundary from the lateral boundary. Okay, so this is what I call S sub A. There could be more than one, so you take the one that is most to the left. Okay, so the one that is most to the left, you call it X sub A. So what information do we get along this curve? We know that Ux here has to be greater than or equal to 0, okay, by construction. And so with this information, so over here, Ux is greater than or equal to 0. Over here, Ux, we know it satisfies the lower bound, okay? So it satisfies what we want. And so the next step is, okay, let me see how I can prove an estimate like this over here. So we use a barrier, okay? So we use a barrier, we call this A. Over here, we define a function that is a solution to the heat equation. It is equal to Ux on the boundary, and it's 0 on the bottom, okay? And this is what we want it to be very close to Ux. Now, since this is, since V on the lateral boundary satisfies these bounds, we can show, okay, so I'm going to skip the details here, we can show that the infimum, okay, a little bit more inside, is bounded below. Okay, so finally, the last step is, now we know V satisfies the bound that we want, and we expect V to be close to Ux, okay, whenever this is very close to 0. So we just need to choose the A, okay, so the level set, sufficiently close to the 0 level set in a universal way, okay? So everything boils down to doing things universally, okay? And so this is just a picture. The key step is to prove something like this, okay? That you can quantify universally how close this is, and it's enough to find a time for which this is true. Okay, so this is something that we show, and once you have that, again, you can use one of these global barriers to prove that V minus X is small as you want, choosing A universally small. Okay, this is roughly the idea. I don't want to get into too many details. Okay, so that would prove the non-degeneracy. And then the last part is, well, what about the regularity of the free boundary? Okay, so we show first that, so it's a graph, okay, for later times, and it's the function is C1/2. And to do that, the idea is to use the holograph transform. So this is something that Marvin mentioned in his talk that didn't work for him due to the non-local effects. For us, it works really well. And so, okay, so if you've never seen this tool, very quickly, let me explain what this does. So the idea is, let's say this is 0, 0, okay, and I'm going to apply this transformation in a neighborhood of it only on the positive phase, okay, where I know that I have regularity. And so I'm going to do a change of variables. I'm going to call y u. And I can do this because of the monotonicity, okay? So really, let's say the difficult part was the previous theorem. So I do the change of variables, and I define h, the holograph transform, as the function satisfying this implicit equation. Now, what is this doing? Well, y is basically flattening all level sets of u, right? So you take the 0 level set, and it's mapped to y equals 0. Let's say the A level set, and it's mapped to some y equals b. Okay, and now u is positive here, and it satisfies the heat equation. And this is satisfied pointwise, right? The u is smooth in the interior. So what does H satisfy? You can actually compute, you can take derivatives in the classical sense, and it will satisfy this equation. Okay, so this transformation, the advantage is that it flattens, right? It flattens the free boundary. So it transforms the problem of studying the regularity of a free boundary problem into the regularity of a flat boundary value problem. That's the main advantage. Now, of course, you have to pay some price, which is not too bad. The price is that the equation satisfied by H is nonlinear. You started from a nice equation, but let's say bad boundary. Now you have a nice boundary, but you have a sort of bad equation, but it's not bad. It's not bad because thanks to the non-degeneracy and the Lipschitz continuity, you know that this coefficient is actually bounded above and below. So this is a uniformly parabolic equation. Okay, so it's really not that bad. And so you basically study the Schauder theory, the boundary regularity of this solution. Okay, so we proved that H restricted to y equals 0, which is exactly R of t, is C1/2. Okay, and then you're done, right? So if you plug in here y equals 0, this is R of t, right? And so that's just what you're trying to show, that R is C1/2, okay? And lastly, what about the optimality? Well, coming back to this example that I told you at the beginning, we will come back to this. Okay, so we proved that the free boundary has to be C1/2. Can it be better? The answer is no when you have a jump discontinuity. Okay, so if you have a jump here, then this will behave like a square root. Okay, and we don't really prove this for this explicit example because finding explicit solutions to the heat equation with this, prescribing this curve here, well, I don't know how to do it, but we are able to show that, so there's a pair of functions U and R that satisfy the elliptic parabolic problem, and R is comparable to the square root, okay? And in this construction, we prescribe this jump discontinuity, okay? I mean, this is really what's happening. Okay, so future work, so to wrap up. So like I said at the beginning, there's not much done in higher dimensions, right? All of this was one-dimensional, and really, we used strongly this property here, right? I mean, if you work in higher dimensions, you cannot use this. So it would be very interesting to study the problem in higher dimensions. Something that we did study with Dennis was, okay, so can the free boundary develop singularities? This is something that people study, for example, in mean curvature flows, right? So if you start with like an initial profile that is smooth, can it create singularities? And what we proved is that if you start with something that looks like a dumbbell, then the neck is going to collapse. Okay, so that's an interesting observation here. And then something to do, so an open problem would be to study this local regularization for free boundaries in this higher dimensional setting. And here this is, I mean, completely open, and I think it would be very nice to tackle this problem. Okay, so I'm going to, and only global results are known for monotone flows. Okay? So yeah, that's it. Thank you for your attention.